Nice. So yeah, state sync. Please give us the context what state sync is, why we generally do it in our protocol, what is the purpose of it.
Let me share some documentation. Yes, this looks right. So, answer to this question is mostly documented. We have a page called How Sync Works. It describes all kinds of syncs we do, all kinds of sync a node needs to do if it starts when it is far behind or not so far behind. And in one other case, which we will cover in a second. So if your node is very far behind, first it gets all the headers so that it has a complete chain from Genesis to the head, and it can verify that all headers are created one after another without skipping, without inserting anything fake, because blockchain. Next block contains the hash of the previous block. So, step 1, header sync, relatively simple. Step 1a, not implemented. We will not cover it now. Step 2, state sync. This is needed for the case when you have a lot of blocks, when you are behind by a lot of blocks, namely a few epochs, and to avoid the terrible work of processing multiple tens of thousands of blocks or even hundreds of thousands of blocks, you can just download some well-known. You can just download state corresponding to some well-known point in time and continue processing the remainder, which is not so many blocks from that well-known point. What state sync does is it lets you download state at the beginning of the current epoch, and then you only need to catch up in that epoch by processing a few thousand blocks, which is relatively fast.
Cool.
That's scenario 1. And scenario 2, you are a chunk-only producer who exists only to produce chunks. You configure the node to not track any particular shard. So you kind of start a node that tracks nothing. But as you join and stake, the protocol will tell your node to produce chunks for a subset of shards. And the next epoch, you will need to have the state of those shards available. And maybe a few epochs from that time, you will need states of different subset of shards. And how do you switch? You don't want to go back in history because you explicitly said you don't care about state of shards. You only want to produce your blocks, your chunks. And so you download well-known states, states corresponding to well-known points in time, which is the beginning of the epoch. You process blocks for that subset of shards, and you have up-to-date state when the epoch switches, and you can produce chunks when they are expected from your node.
Okay. So the second scenario seems like crucial and unavoidable. The first scenario is still not happening on at least archival nodes and can be avoided on RPC nodes. And that's what we're doing right now. So right now, state sync is disabled. Why?
So archival nodes don't need it because archival nodes need to have all state after each block, and they need to have each block. Yes. RPC nodes avoided by downloading a recent snapshot we provide on S3. Internal nodes get snapshots instantly from GCP. Very convenient. And we disabled it today because state sync is not in a good state, because our state is 100 gigabytes on testnet, maybe 50 gigabytes on mainnet. And to make all this state available to a single peer that wants to sync, multiple hours, if not tens of hours of computational work needs to be completed by its peers. And we know that making the state available is such a computational burden that validators actually see impact on their uptime, that therefore they throttle requests for state syncs. Therefore, you can't possibly get mainnet state today if you ask validators to give you any bits of state. And
Interesting.
testnet, it's just huge. It's just...
Yeah.
Okay, to show you how big it is, I have a graph. I have an experimental node which has dedicated threads to each shard, which constantly creates all the parts of state and writes them to S3. Doesn't matter where exactly it writes them, but what matters, I hope you can see the graphs. The orange line is shard 3, left side is testnet, right side is mainnet. And you can see that this orange line is moving up very slowly on both graphs. And it shows that it takes you in mainnet maybe 3 epochs to dump a single state of shard 3. On testnet, it takes you, I don't know, 10 epochs maybe to dump state of shard 3. Yes, you cannot expect your peers to do all this computational work to sync a single node.
And my understanding, because state on mainnet, like state column on mainnet, is much bigger than state on testnet, and it is not.
Not. Testnet shard 2 and 3 are 50 gigabytes, and all of mainnet is like 40, 50 gigabytes, all shards.
I said 70, but okay.
It's like plus or minus, maybe 70. I don't remember exact numbers, and they will change. Today is March 2023.
Okay. So I think the problem with shard 3 on testnet is that it's Svetcoin shard, right? And
Right.
And I don't know what the problem with shard 3 on mainnet, but even
it's also Svetcoin.
Oh, okay. So we just cannot fix this problem by resharding evenly, like having a lot of smaller shards, because we always will have a huge Svetcoin, right?
I don't know, maybe, but this is not a viable, the feasible solution that we can easily implement.
Yeah, I understand. It's just
we have.
Yeah, we will always have an unproportionately huge shard. It's what I'm saying, and we cannot expect all shards to be even.
I hope it will not be the case necessarily, but we have to work with unproportionally big shards we have today.
Okay, so talk a bit about the solution that we have right now, that we are working towards implementing.
Okay, we have a design doc called Go State Sync v2, and it says that to make state sync work, make it great, make it revolutionarily new, more scalable, performant, and reliable, what we need is to make the dumps of shards take not 70 hours, but maybe 2-3 hours. That would be fantastic. And I see 2 dimensions, vertical and horizontal, to make it, to speed it up. By vertical, I mean, let's use flat storage to generate dumps of state. And there is a prototype from Marcin who left us that if you read flat storage, it actually takes you maybe 10 times, it happens maybe 10 times faster, which is understandable because all those nodes, you need to do a lot fewer random lookups to get the states corresponding to sub-trees you want to export. And all this concept of state parts that need to be sub-trees, we can also examine and reconsider. But flat storage opens up a lot of possibilities. Exporting sub-trees was natural when the whole state is a tree. Why not split it up into sub-trees and then just merge it? With flat storage, we'll think about it again. But good that we have a prototype which is 10 times faster.
That's nice. What is the horizontal?
Horizontal dimension Why not use multiple nodes to dump the same state of the same shard to some well-known place like S3? So you could roughly use 10 machines, maybe 100 machines, and make it, I don't know, 100 times faster. That would be nice. On top of making the process 10 times faster by itself. So that lets us reduce the wall clock time until the dump is complete and nodes can use it to sync. And using flash storage will let us decrease computational work needed to generate a dump.
Okay. I, for some reason, thought that it was either or scenario where we either approach like vertical scaling or horizontal scaling, but yeah, it doesn't make sense not to pair it. Yes. So can you show us some code that illustrates state sync algorithms, main stages, what the node goes through just to sync one shard?
Okay. So part 1, client actor determines if a node needs to sync. It chooses if it needs the header sync, block sync, state sync, all of that.
Mm-hmm.
Somewhere. Anyway, yeah, exactly this. So if sync is needed, and I'm not currently syncing, let's see what is going on. Header sync happens always when the node starts unconditionally. Then we check if state sync is needed, and to do this, we go to the there is a function which tells you when it's happening, and one of this horizon. Oh. So the condition for triggering state sync, it's an interesting one because it's not a fixed amount of blocks.
Mm-hmm.
It's this. It says that header head and head are at least in different blocks.
Mm-hmm.
And if I read this correctly, header head is at least, sorry, not in different blocks. Header head is at least in 2 different epochs. Like the not in the next epoch and not in, but at least in the next epoch. That's what I'm reading.
Okay, yeah.
So they are not the same, and not even the next epoch, because catching up to the next epoch may be a matter of a single block. So it needs to be at least one full epoch behind to trigger state sync. But there is also a condition that maybe your epochs are artificially short, like 5 blocks, and then there is an extra constant on top of that to make sure it doesn't happen too often. Yes, that's the condition for triggering state sync. Yes. So then how it works. If it's needed, the state sync object is created in the client. Then client actor. I don't understand why client actor is driving this part, but it is. Maybe there is a good reason. I haven't thought about it. So it checks what's the status. If it's state sync, then okay, let's proceed with state sync. And state sync itself is a state machine. It has several different states. No pun intended. Yeah, several different states. And you can roughly see them represented as shard sync status.
Mm-hmm.
So if I need a header, if I need parts, if I'm scheduling the parts to be applied, the difference between applying and scheduling I don't understand, and then complete. And an extra step for doing state split if resharding happens. In that part, I haven't looked. That is complicated, and also if you're changing shard layout, you cannot do state sync the next epoch, and I totally understand why not, because it's a corner case which doesn't happen often but hard to handle.
Mhm.
Yeah, maybe we should handle it, but let's get back to it. So, state 1. What I didn't mention is that the state needs, first you need the header. The header represents the state, the root of the tree of your shard. So that this well-known point in time that you dump and that you apply changes to, and contains also the last chunk of the previous epoch and some proofs so that you could verify that this is all legit and not made up.
Mhm.
But mostly, as soon as all you need is state root and to believe in this state root. Second part, you get the part. Second step of this state machine is to get the parts which combined give you the correct state. Currently, state parts are hard-coded to be 1 megabyte in size. So shard 3 of testnet requires 50,000 parts to be downloaded. Today, that's a lot of parts, yes. That's a lot of even simple network delays to send the request and get the request.
Yeah.
Mhm. So status of every part is tracked separately. GitHub. No, this one. Yes. Then for each part, it's tracked when the request was made, who was the target of my request, and I believe only one request for part is sent at a time. And only if everything is correct, we're moving to the next stage, which is scheduling. So in scheduling, what we say is, so I have all the parts. Let's start another thread that only works on applying those parts one by one. Yes, and it calls some task scheduler. And to see what the task scheduler is, you need to go 3 levels up the stack. But it basically uses one of sync job actors to run a loop over every part ID to apply it.
Mhm.
And so after you're done applying, you have the state. And you can skip all of that. You're basically done.
Do we validate anything after we download the state, like just the hash, right?
Even when we have the part with validated, the part represents a tree such that from the given root I can reach all the nodes contained in that part. The nodes contain sizes, so you can at least verify that if you have the full subtree, that sizes of that subtree matches, and because keys are hashes of the nodes,
Mhm.
so hash of the node kind of hashes also the children. It is very hard to fake some data in this tree, so it does validate that the tree itself is correct. And when you have the global, you combine the full state, yes, you can verify that the root of the tree is a hash, and that hash indeed matches what you were expecting.
Mhm.
And if it doesn't match, then you delete all state parts and you start from the beginning.
And if you restart, you also delete all the state parts and start from beginning, right?
If you restart what? If you
The
restart
node.
the node?
No?
No, if you restart the node, the progress is carefully tracked per part. So if you restart, the progress is persisted. But for a long time, we had an issue that looked like there is a database corruption, but there is no. It was just a matter of unwrapping some network code which expected some block to be available. But as soon as you remove it, you restart, you have the progress per state part, and you can happily keep downloading parts. Or in case of what happens if you restart when the parts are being applied, I haven't tested, but it seems that they will be rescheduled and reapplied. But yes, I haven't tested that part.
But downloading parts right now is a matter of downloading them from S3. Will be matter of downloading them from S3.
Yes.
As a single part, or like as like a huge file with all of the parts?
But the moment it is files of 1 megabyte size, so shards can require 60,000 parts to be objects to be downloaded.
That seems like it's gonna break something. When something triggers many nodes to restart at the same time, so maybe several nodes, maybe we have a huge database migration, and several nodes will undergo this huge database migration, emerge from this very late, and go to S3 requesting bajillion files each, roughly at the same time. What will happen then? Will S3 handle it if it's the same files? I know that S3 is like a powerful outside corporation of Amazon, but still.
I expect it to handle it. I also expect Pagoda to pay a lot of money to S3 for all this egress traffic. We already paid them a lot of money for storing and serving all our database snapshots. So that should work. Sometimes S3 bans you for a minute or two saying you have too many requests, but we can introduce timeouts, retries after some, I don't know, minute or so should be enough to make reasonable load on S3. That seems like solvable problems, solvable by paying a lot of money to Amazon.
Okay.
And in the future, it would be really nice if we could decentralize this approach to somehow incentivize the community to obtain generate state parts in advance, to make them available, and to serve state parts to other nodes which need syncing, or to chunk producers which want to switch from one shard to another.
Okay, last question. I know that the dream is to have an RPC node start from Genesis and in the matter of 10 minutes, or I don't know how many, but like minutes, be able to produce everything, new blocks, be in sync. But what is an achievable dream for like next 6 months?
Even what you describe is not out of reach if we implement Epoch Sync, and we don't plan to implement it in the next 6 months, unfortunately. Epoch Sync is basically very fast header sync because you don't download even 1% of headers. That would be really make it faster. A workaround would be to provide a snapshot of database which contains only headers, right? So then you can skip header sync. Beautiful.
Yes.
And you just download state and go where you need to go. That would be achievable in maybe 3 months, maybe 6. And in 3 months, I want a node which is configured to track no shards, which acts as a chunk producer to be able to freely switch between shard 0, shard 2, shard 3, not caring much which shard it is and not avoiding any shard, because our dump process of state sync should be fast enough to handle it.
Okay.
There is also a question of whether our application of state parts is fast enough. Maybe not, but we haven't tested it much because we cannot generate dumps of shard 3. This is a blocker to test an application of state. And yeah, to apply SHA-2 on testnet takes a bit more than an hour.
So basically, in 3 months, we don't see downloading and producing state parts. It will not be a bottleneck.
Production of
Hopefully.
state parts should not be the bottleneck, yes.
Okay. Cool. Thanks for your time. I got to know. I got to ask all that I wanted to ask. I now know more about code, so that's very, very nice. And I hope it will be useful for anybody who is willing to watch it. I don't know if somebody is that clinically insane in our company, but maybe there are some people other than me. Okay. Thanks for your time.
Thank you very much. Nice interview.
Okay.